The main idea of LU decomposition, lower upper factorization, is that you've got some matrix, let's say some matrix A, and you want to split it up into two matrices multiplied together, which is why it's called factorization or decomposition. We're factoring this matrix into a product. In the same way that, for instance, let's say 35 might be factored into 7 times 5. So this would be a factorization of 35. In the same way, we want to factor a matrix A into a product of two matrices. And there are many ways to factor a matrix, but we're looking for a specific factorization that follows certain rules here. In particular, that the U matrix must be upper triangular. And the L matrix must be lower triangular. So we want a purely lower triangular matrix times a purely upper triangular matrix that multiply it back to some original matrix we started with. And what do we mean by upper triangular or lower triangular? How are those defined?
Upper triangular is when like the numbers are above the diagonal and numbers and below the diagonal is 0.
Yeah. And keep in mind, it's defined purely in terms of what's not in the upper triangle. Upper triangle means everything above the main diagonal and above, including the main diagonal. So upper triangular means everything that's not in the main diagonal is 0. So you could have anything in all those other spots. Each one of these as just blank spaces. So the main diagonal and everything above it could be any values. But the important thing is everything that's not in that upper triangle must be zeros. So by definition, any matrix where everything below the main diagonal is all 0, that matrix counts as upper triangular. Note that this doesn't say anything about what's in the upper triangle. It's possible that there are zeros in the upper triangle also. It still counts as upper triangular. Upper triangular is a statement about what's not in the lower triangle. In fact, a matrix of all zeros, this technically counts as upper triangular because everything below the upper triangle, everything below the main diagonal is all zeros. So this matrix does count as upper triangular. And then lower triangular, similar idea, that anything above the main diagonal must be 0. But everything, the main diagonal and below could be anything. So you could have anything you want, possibly including zeros on the main diagonal and below. But as long as everything above the main diagonal is all 0, that matrix counts as lower triangular. Which also means a matrix of all zeros does technically count as lower triangular also, because everything above the main diagonal is all 0, so it counts as lower triangular. And also everything below the main diagonal is all 0, so it also counts as upper triangular. Any questions on those definitions so far? So what we want to do is take any matrix that might or might not have zeros in convenient locations and split it up into a product of these two factors, one that's purely lower triangular, one that's purely upper triangular. And typically the way we do that is to start by row reducing. In particular, we've already seen the idea of using row reduction to turn a matrix into either upper triangular or lower triangular, depending on which direction you're going. You can use row reduction to turn a matrix into upper triangular. So let's start with that. In particular, let's try just a quick example of a 2x2 matrix. Let's say you've got a 2x2 matrix that's just, let's say, 2, 3, 8, 1. So let's call that our original matrix A. If we want to turn that into upper triangular, yeah, the presence of extra zeros in the upper triangle doesn't matter. Upper triangular means everything below the main diagonal is all 0. The definition of upper triangular doesn't say anything about what is or isn't in the upper triangle. So 0 is below the main diagonal means the matrix counts as upper triangular. So for this one, if we want to make this upper triangular, this one I think will only really require one step. To make this lower triangular, or sorry, upper triangular, what value do we need to get rid of?
8.
Yeah, if we can just get rid of this 8, then the rest will be upper triangular. So what row operation will get rid of that 8?
Multiply row 1 by -4 and add it to row 2.
Yeah. So we're modifying row 2 by adding -4 times row 1. And let's see what that turns into. Top row, we're not changing yet. But the bottom row turns into what here?
-11.
Yeah.
Oh wait, 0, -11.
Yeah, we get a 0 from 8 minus 8, and then -11 from 1 minus 12. Does that now count as lower triangular? That is it true that everything below the main diagonal is 0? Or upper triangular, yeah. Yeah, this does count as upper triangular, in the sense that if we circle the main diagonal here, everything below the main diagonal is 0, so this does count as upper triangle. Which means we can stop here and declare this matrix to be U. For a larger matrix, it would take more steps. 1, 0, 2, 0, 1, 0, 0, 0, 1. Let me 1, 0, 2, 0, 1, 0, 0, 0, 1. Would you say this matrix has all zeros in what region? If we take a look at the main diagonal. Yeah, everything below the main diagonal is 0. So how would we describe this matrix? Yeah, this matrix is upper triangular. It has the property triangular. It has the property that everything below the main diagonal is 0. It does not count as lower triangular because we have some non-zero stuff above the main diagonal. If the 2 wasn't there, if this 2 was a 0, it would count as lower triangular and upper triangular, and also diagonal. That is, if everything off the main diagonal is all zeros, then the matrix is called diagonal and also counts as both upper triangular and lower triangular. Any other questions on the definitions so far? So going back to the matrix we got from row reducing, and in this case, because the matrix was pretty small, just 2 by 2, it only took one step to turn it to upper triangular form. For a larger matrix, it's going to take more than one step. But we now know the upper triangular matrix U. So our desired goal here, we want A to equal L times U. We know A because that's what we start with. We just found matrix U. We still need to find matrix L. And one way to do that is trial and error or a guess and check sort of thing. You could write out L as just a matrix of variables. You could say L, we know it's going to be lower triangular. So we've got a 0 above the main diagonal. And let's say these other values are just X, Y, and Z. So one way you could do this is multiply L times the U matrix we found, set it equal to 2, 3, 8, 1, and you get a system of equations you can solve for X, Y, and Z. But that's usually a lot of trouble. And also, as far as multiplying by the inverse is concerned, if we have A equals L times U, you could try to find L by multiplying both sides by U inverse. And that's going to be right multiplying because we want to cancel out the U. So that could work. The only problem is U might not be invertible. Maybe U has some inconvenient zeros that make it non-invertible. In fact, U doesn't necessarily have to be even a square matrix. If A is not a square matrix, U won't be either. So multiplying by U inverse is a good thought, and sometimes it does work, but it can't be guaranteed. So instead, we're going to need a more general method. And one way to do that, the usual way, other than the brute force, plug in some variables and try to solve for them, which takes a while and is rather tedious. Instead, often a much more convenient way is to take a look back at the operations we did. And you want to be very careful to keep meticulous track of all the operations it takes. In this case, just one, so that makes it easier. We talked about a little bit about this earlier, that we can write this operation as an elementary transform matrix. We can say that we take that matrix A, this operation can be written as an elementary transform matrix. Let's call that E1. In the sense that it's the first, and in this case, the only transformation matrix we use. And we want that to equal, in this case, matrix U, which was 2, 3, 0, negative 11. So how can we write this operation in the form of an elementary transform matrix? What values here are going to turn this original matrix into the result? One, 0, because that says don't change the first row. And then how would we write modify the second row by this procedure, the adding -4 times row 1 to row 2?
-4, 1.
Yeah. Because again, if you think of this as a recipe or instructions for building the new second row, we're taking -4 times something from row 1 plus 1 times something from row 2. And that applies to every column. So we get -4 times the entire first row plus 1 times the entire second row. In other words, we're taking row 2 exactly as it is and adding -4 times the first row, which is exactly what this step is all about. So that's our elementary transform matrix. And note that that is lower triangular. Everything above the main diagonal is 0. In general, anytime you're using a transformation that only uses higher rows to modify lower rows, the elementary transform matrix will always be lower triangular. So we at least have a lower triangular matrix times A equals an upper triangular matrix. But that's not quite the format we want. We want the lower triangular matrix to be on the other side. So how could we get rid of this matrix and institute a matrix over here instead? Which part? That we want a lower triangular matrix over here instead of over here?
The statement about the upper and lower triangular, like where you related to, I think it was U.
Yeah, the U is an upper triangular matrix, the one we got from the row reduction in the first place.
It was like a rule that you said like one has to be upper triangular and the other one lower, something like that. Like E is lower and then U is upper.
Yeah, the elementary transform matrix, which represents this row operation, as long as the elementary transform represents using a row from higher up to modify a row from lower down, then the elementary transform matrix will always be lower triangular. For instance, in this case, we used the top row to modify the bottom row. So that means this looks just like the identity matrix, except with a -4 down here. So anytime you're using a row operation that's using a higher row to modify a lower row, like adding row 1 to row 2, or adding something times row 2 to row 5, using a higher row to modify a lower row, the elementary transform matrix that does that will always be lower triangular. Because you can always make an elementary transform matrix by starting with the identity matrix and doing that change to it. So if you add -4 times the first row to the bottom row, you get a -4 below the main diagonal. Everything above the main diagonal is still 0. So this counts as lower triangular. And this is why we're specifically only using higher rows to modify lower rows, because that guarantees that all of the transform matrices we create will be a lower triangular. Any other questions on that so far? The problem is, though, we want A equals L times U. What we have is E times A equals U. So how could we get rid of this E here?
We get the inverse of E.
Yeah. If we multiply both sides by E inverse, specifically if we left multiply both sides by E inverse, then that means E inverse and E will cancel out, so we'll have just A. And the reason this works in the first place is that E represented a operation that can be undone. Anytime you're just adding a multiple of a row to another row, you can undo that. In this case, what's the opposite of adding -4 times row 1 to row 2? That is, what would be the inverse of this matrix?
1 would be, instead of adding 4, instead of subtracting 4, adding 4.
Yeah, because we just subtracted 4 times row 1 from row 2. We can put that back to the original by adding 4 times row 1 to row 2. So that means E inverse, or E1 inverse, is going to be exactly the same, but with a +4 instead of a -4 here. Because E1 had the effect of subtracting 4 times row 1 from row 2, we can undo that and put the matrix back to the original by adding 4 times row 1 to row 2. So these matrices should be inverses. And if you're not sure, you can always check by doing what? How can you always verify that two matrices really are inverses?
You multiply them to see if we get the identity matrix.
Right. So if you're not sure, you can always multiply them together. E1 times E1 inverse should lead to the identity matrix. And that should be true no matter what order you multiply them. So we've got E1 inverse and E1 canceling out, because that's just the identity matrix times A equals E1 inverse times U. And E1 inverse is lower triangular. So E1 inverse is L here. So we now have L also. So we now have a lower triangular matrix, 1, 0, 4, 1, and an upper triangular matrix, 2, 3, 0, -11, that should multiply out to the original matrix A, 2, 3, 8, 1. So that's our LU decomposition here. And we would write that, the final result, as A equals L times U, A being 2, 3, 8, 1, L being 1, 0, 4, 1, and U being 2, 3, 0, -11. So U is the upper triangular matrix we get from row reduction. L is a matrix composed of the inverse of any operations we did to get there. And as always, you can do one final check, multiply these together, and make sure you get back to the original matrix. Because the whole point is that these should multiply to the original matrix. Any questions on that factorization so far? And I want to emphasize that this factorization is not unique. It's possible to split up A into a different L times a different U that still follow the rules that this is lower triangular and this is upper triangular, but they still multiply to this matrix. So there are many possible LU factorizations. If you go through this exact procedure, row reduce, and then write any operations you did as an elementary transform matrix, it should get to the same result because it's the same procedure. But there are other ways to split it up into a different L times a different U that still work. So this is not unique. There are many possible answers. As long as you have a lower triangular matrix times an upper triangular matrix that multiply to the original, that is an LU factorization or LU decomposition of the original. Any other questions on the theory of why this works? And in this case, this was made a lot simpler by the fact that it only took one step to row reduce. Because we just had a 2x2 matrix, we just needed to make one modification to turn it into upper triangular. For a larger matrix, it's going to take more steps. So let's see how things might be different if we have a larger matrix. Let's say A happens to be 3x3. In fact, let me pull up a quick example here. Let's write it down. Let's say 2, 2, 3, 4, 1. In this case, how many steps would you expect it to take to reduce this to upper triangular? We can't do it in just one step anymore because it's a larger matrix, but how many steps would you expect it to take?
Around 3 steps.
Yeah, probably 3 steps. We can use the pivot of the first row, this 2, to eliminate the 4 and the 7. That'll get us 0 here and here. And then we can use whatever's remaining here to eliminate the whatever's below it. We've got 3 values we need to cancel out, so it's probably going to take 3 steps to do that. So in terms of the notation we were using earlier, you've got matrix A. You're going to need to modify that by an elementary transform matrix, and then another one, and then a third one. Because each one of those row operations can be written as a separate elementary transform matrix. So you've got A, you modify it by multiplying by a transform matrix, then that whole thing can be modified by multiplying by another transformation matrix. And then that whole thing can be modified by multiplying by a third transformation matrix. And that should make it multiply out to some purely upper triangular matrix. So our row operations can be written as 3 matrices applied left, left, and left to matrix A. But we want to get A equals something times U. So how could we get rid of these 3 matrices?
Multiply the inverse to both sides.
Right, we're going to need to multiply by their inverses, but we've got to be very careful about order. Based on this structure, what's the first inverse we would need to multiply by? If we multiply both sides by E1 inverse, can these cancel each other out? Yeah, we're going to need to start with E3. If we've got these matrices in this order, E1 inverse times E3 doesn't really do anything useful. And we can't just rearrange the order to put the E1 inverse next to the E1 because matrix multiplication is not commutative. So instead of starting with E1, let's start by multiplying both sides by E3 inverse. That way, E3 and E3 inverse, since they're being multiplied directly by each other, those do cancel each other out, leaving just the identity matrix. And then after that, what would be the next inverse we'd multiply by? Yeah, now that these are gone, we've got just E2 that's actually accessible now. So if we multiply both sides by E2 inverse, now we can say that E2 inverse times E2 cancels out. And then what would be our last step here? What else do we still need to cancel out here?
E1 inverse.
Yeah. So now I would multiply by E1 inverse. on both sides. And at this point, we now have E1 inverse directly multiplied by E1 because all this other stuff is gone. So those do cancel out. And it looks like all that's left is A equals, in this particular order, E1 inverse times E2 inverse times E3 inverse times U. And again, if we set this up right, all of these elementary transform matrices will be invertible, and they will also be lower triangular. So when we multiply all those together, the result is also lower triangular. This is an important property of lower triangular matrices. If you take the inverse of a lower triangular matrix, the result is still lower triangular. If you multiply some lower triangular matrices, the result is still lower triangular. This also applies to upper triangular as well. So we can call the product of these inverses in that order L, and then we still have U as it was from the row reduction. And there's our LU factorization, or at least a possible LU factorization. So generally what you want to do, at least as one method to do this, row reduce this until its upper triangular form, keep track of all the steps you took, all the row operations, write each of those row operations as an elementary transform matrix. The inverses of those transform matrices in this order will give you the lower triangular matrix L. Any questions on that so far? And let me make a note of that. Matrix U is just obtained from row reduction. Matrix L is the product of the inverses of all of the elementary transform matrices you use for the row operations in this particular order. So starting with the first one you used, inverse, and then right multiplied by the next one inverse, then right multiplied by the next one inverse, possibly more if it was an even larger matrix and took more steps. But the lower triangular matrix can be the elementary transform matrix inverses in that order. How do we know? Just by looking at the problem? You can't necessarily always tell. In this case, I would assume it's 3 because you need to eliminate 3 numbers. So presumably you use this 2 to eliminate the 4 and use the 2 to eliminate the 7. Then you take a look at whatever number remains here after that row operations and use that to eliminate whatever number is here. It's not necessarily that many though. 3 I would think would be the maximum. It might be the case that by coincidence, when you use this 2 to eliminate this 7, maybe this number also happens to eliminate this number and you already have a 0 there. So it might only take 2 steps. Or if you started with zeros already in these positions, maybe it'll only take 1 step. So the 3 here is more of a maximum. It's going to take at most 3 steps to eliminate these 3 numbers. If it was a 4x4, we still want to eliminate everything under the main diagonal. And it looks like that means we would need to create zeros 1, 2, 3, 4, 5, 6 locations. So if it was a 4x4, I would expect it to take up to 6 steps to eliminate everything under the main diagonal. Again, it might be fewer than 6 if more numbers happen to cancel out while you're going through the first few steps, but at most 6. Yeah, for a 3x3, it would be at most 3 steps. You can also sometimes run into some complications, like if your first row operation accidentally gets some extra zeros, maybe the 4 cancels out and the 1 also happens to cancel out. In that case, you couldn't use a 0 to eliminate something non-zero here. So how do you think you would address that? If you get an extra 0 you didn't want, and now you can't use that to eliminate what's down here, how could you rearrange that to still get an upper triangular result?
I can swap the rows.
Yeah, you can swap some rows. You can apply a permutation matrix. In that case, you wouldn't just have the elementary transform matrices, you'd also have a permutation matrix P. So instead of having just LU decomposition, you'd have PLU decomposition, a permutation matrix times a lower triangular times an upper triangular. So that's usually called PLU decomposition or LPU decomposition, depending on whether you do the row swap at the beginning or at the end. Like you could row reduce and then realize, oh, I'm going to need to do a row swap and do the row swap at the end. Or once you notice you're going to need a row swap, you could go back to the beginning, do the row swap first, and then row reduce. So that just makes a difference of whether you get LPU or PLU, depending on which order you apply the permutation. So if that's necessary, if you can't get it to upper triangular form without a row swap, then that means that matrix has no LU factorization. But it can still have an LPU and a PLU factorization. It'll just need that row swap at some point. Any questions on that so far? So let's try out the row operations here. See if we can get this into factored form real quick. From this starting point, what would be your first operations to row reduce this?
Multiply row 1 by -2 and add it to row 2.
Yeah, row 2, we're adding -2 times row 1. Let's see what that's going to look like. First row doesn't change. Second row, we got 4 minus 4, 1 minus 4, and 6 minus 6. So we get a 0 there. And then formally, we should do this as a second step, but I think we, as long as we're careful about what order we're doing it in, we should be able to combine this into one step. What operation will take out this 7? What multiple of row 1 would we have to add there?
-7/2.
Yeah, if we add -7/2 times row 1, -7/2 times 2 would be -7, which will cancel out this 7 here. So let's try that out. 7 minus 7/2 of 2 is 7 minus 7, so that's 0. 1 minus 7/2 of 2, that's 1 minus 7, so that's -6. And then 0 minus 7/2 of 3, that's -21/2, which will just leave us a fraction there. Any questions on that so far? And then one more step. We've used this 2 to eliminate everything else in that column. Next, we want to use this pivot, the -3, to eliminate everything else in that column. So what operation could we do to row 3 that would get rid of this -6?
Multiply row 2 by -2.
-2 times row 2 should do it. That way we get first row is not changing, second row is not changing. Third row, we've got nothing plus nothing. -6 plus 6 is 0. And -21/2 plus -2 times 0 is still -21/2. So this would be upper triangular. So we would call this our matrix U. So U is this final result of the row reduction process, once we've got it to purely upper triangular form. So let me make a note of that here. A equals some lower triangular matrix we don't know yet, times this upper triangular matrix 2, 2, 1, 0, -3, 0, 0, 0, -21/2. And it doesn't matter that we happen to have a 0 here. The important thing is the entire lower triangle, everything below the main diagonal is 0. So this is matrix U. Any questions on that process for finding U so far? And then to find matrix L, we can go back to the steps we took, the 3 row operations, and use those to build matrices E1, E2, E3. So for E1, what's the matrix going to look like if all we want to do is add -2 times row 1 to row 2?
One, 0, 0, and then -2, 1, 0, and then 0, 0, 1.
Yeah, because that way we just have exactly the identity matrix except with this one modification. So that means the new second row is -2 times the original first row plus the second row exactly as is, plus no information from row 3. So this is the first elementary transform matrix, E1. The second one, we can also use the framework of start with the identity matrix, but what's the one change we're going to have? What's the one difference?
Instead of -2, it's -7/2.
Right. And also that -7/2 would go in which position in this matrix? Which row are we modifying?
The third one.
Yeah. So we'll have a -7/2 in this position in the third row, and then zeros everywhere else. So this matrix signifies don't change the first row, don't change the second row, but modify the third row by taking -7/2 times the first row plus the third row exactly as is, and no information from the second row. So that's matrix E2, 1, 0, 0, 0, 1, 0, -7/2, 0, 1. And then E3 is supposed to represent this transformation, adding -2 times row 2 to the third row. So again, we can start with the identity matrix as a framework. We're going to make one change, which is going to be a -2 in which position here. How would we say we're modifying the third row by adding a multiple of the second row? Yeah, third row, and which position in the third row? Or what would our new third row look like? Yeah, exactly. -2, or sorry, yeah, 0, -2, 1, and zeros everywhere else. So this looks mostly like the identity matrix. 1, 0, 0, and 0, 1, 0 say don't make any further changes to the first and second rows. But the third row is 0, -2, 1. That's saying take no information from the first row, but take -2 times the second row and add it to the third row as is. So this represents exactly this change. We now have all three of our transformation matrices, but what we want to build L is the inverses of all of them. How do we change all these really quickly to their inverses without even needing any further calculations?
You make them all positive.
Yeah, you can just take all of those modifications. These happen to be negative, so we'll make them positive. Or in reverse, if this modification happened to be positive, we make it negative. So in general, take the exact opposite of whatever those modifications are. E1 inverse is just going to have a +2 instead of a -2. E2 inverse will have a +7/2 instead of a -7/2. And E3 inverse is going to have a +2 instead of a -2. Everything else is the same. It still looks like the identity matrix with one modification. It's just that modification should now be its opposite. And then what do we do with those to find matrix L? Yeah, we multiply them together, and specifically in that order: E1 inverse times E2 inverse times E3 inverse. So L is going to be E1 inverse times E2 inverse times E3 inverse. And since we have three matrices multiplied together, you can use the associative property. You can multiply 1 times 2 first, and then multiply that result times 3. Or you can multiply 2 times 3 first, and then multiply E1 times that product. So you can't rearrange the order, but you can choose which pair to combine first. And you could multiply just straight across 1 times 2, and then that result times 3. But I find it's often easier to multiply 2 times 3 first, because then you can take advantage of the fact that this is still an elementary transform matrix. This just says, don't change row 1, don't change row 2, but modify row 3 by adding 7/2 times row 2 to it, or sorry, 7/2 times row 1 to it. So these are going to combine into 1, 0, 0 says, don't change row 1. 0, 1, 0 says, don't change row 2. 7/2 0 1 says do modify row 3 by adding 7/2 of row 1 to it. So if you take row 3, but add 7/2 times row 1, that's 7/2 0 0 plus 0 2 1. So we just get 7/2 to 1. So that's the result of these two multiplied together. Or you could just multiply them row by column as you usually do. You can just use the fact that it's an elementary transform matrix as a shortcut. Likewise, this E1 inverse. This is saying keep the first row and third rows the same, but modify the second row by adding 2 times the first row. So 2 times the first row would be 2 0 0. Add that to the second row, we get 2 1 0. So our L matrix is going to be 1 0 0, 2 1 0, 7/2 2 1. So that's L times U. This is purely lower triangular because everything above the main diagonal is 0, purely upper triangular because everything below is 0. And again, as one final check, you could multiply these together, make sure you get back to the original matrix. So that is the LU factorization of the original matrix. Or I should say one LU factorization. There are many possible, this is just one of them. It's not unique. Any other questions on that? All right, give this a try with, oh, sorry, go ahead.
Oh, so I was just wondering, so do we have to do it where we find the upper triangular matrix first? What if we did like lower triangular matrix first?
I think it would be possible. It would just, actually, I think then you would end up with U times L instead of L times U. So it would be possible, it's just not the result we're looking for. It would be a different factorization. You're welcome. So give this a try with some examples. You can literally just make up any matrix you want. It doesn't even have to be a square matrix, although that usually is what we apply this to. So any matrix you want, apply this same sort of procedure, and you should be able to get the LU factorization. And of course, you can check that by multiplying those together and making sure you get back to the original. So that's one of the things I like about this. You can always check your answer without even needing a solution key. So give that a try with some more examples, and I will see you next time.